In a vacuum, are electromagnetic waves the same at 300,000 kilometers per second regardless of wavelength and frequency? In a vacuum, the speed of electromagnetic waves remains constant at 300,000 kilometers per second regardless of wavelength and frequency. This is known as one of the fundamental constants of the universe. Electromagnetic waves consist of oscillations in both the electric and magnetic fields. The electric and magnetic fields oscillate perpendicular to each other, and these oscillations propagate waves by inducing each other. In a vacuum, where there is no material to affect the oscillations of the electric and magnetic fields, the speed of electromagnetic waves is maintained at a constant rate. However, in the presence of a material medium, the speed of electromagnetic waves decreases. This is because the material absorbs and re-emits the oscillations of the electromagnetic waves, resulting in energy loss. For example, in water, the speed of light is approximately 225,000 kilometers per second, which is about 25% slower than the speed in a vacuum. Therefore, in a vacuum, the speed of electromagnetic waves remains constant at 300,000 kilometers per second, independent of wavelength and frequency. So do radio waves and gamma rays both have the same speed? Yes, in a vacuum, both radio waves and gamma rays propagate at the speed of 300,000 kilometers per second. Radio waves and gamma rays are both types of electromagnetic waves, differing only in their wavelength and frequency. Radio waves have the longest wavelength, while gamma rays have the shortest. However, in a vacuum, the speed of electromagnetic waves remains constant regardless of wavelength and frequency. Therefore, both radio waves and gamma rays propagate at the same speed. Of course, in the presence of a material medium, the speeds of radio waves and gamma rays may vary. Nevertheless, in a vacuum, it can be stated that the speed of all electromagnetic waves is uniform. Does the photoelectric effect also appear in radio waves? Or does it only appear at wavelengths shorter than visible light? The photoelectric effect is a phenomenon that occurs when the frequency of light vibrations is greater than a specific vibration frequency of the material. Therefore, the likelihood of the photoelectric effect occurring is higher for light with shorter wavelengths. Radio waves are electromagnetic waves with wavelengths of 1 meter or more. Consequently, the frequency of radio waves is much lower than that of visible light. Therefore, the photoelectric effect does not occur with radio waves. For the photoelectric effect to take place, the frequency of light vibrations must exceed the material's work function, which is the minimum energy required for the material to emit one electron. Hence, materials with lower work functions have a higher probability of experiencing the photoelectric effect even with light of shorter wavelengths. The work function for metals is typically around 1 electron volt, while the vibration frequency of visible light is approximately 10 electron volts. As a result, visible light, with its higher frequency, can induce the photoelectric effect in metals. On the other hand, the vibration frequency of radio waves is much lower than 10 electron volts. Therefore, radio waves cannot surpass the work function of metals, and the photoelectric effect does not occur with radio waves. In conclusion, the photoelectric effect does not occur with radio waves. So, how high does the frequency have to be for the photoelectric effect to occur? For the photoelectric effect to occur, the frequency of light vibrations must exceed the work function of the material. The work function is the minimum energy required for a material to emit 1 electron. Therefore, materials with lower work functions have a higher probability of experiencing the photoelectric effect even with light of shorter wavelengths. The work function for metals is typically around 1 electron volt, while the vibration frequency of visible light is approximately 10 electron volts. Consequently, visible light, with its higher frequency, can induce the photoelectric effect in metals. In summary, for the photoelectric effect to take place, the frequency of light vibrations must exceed the work function of the material. For example, if the work function of a metal is 1 electron volt, the frequency of light vibrations must be above 1 electron volt for the photoelectric effect to occur. However, even if the frequency of light vibrations exceeds the work function, the photoelectric effect may not occur if the intensity of the light is too weak. If the light's intensity is too low, the energy carried by the light may not surpass the work function of the material, preventing the occurrence of the photoelectric effect. In conclusion, for the photoelectric effect to occur, the frequency of light vibrations must exceed the work function of the material, and the intensity of the light must be sufficiently high. So, is the photoelectric effect difficult in infrared light? Yes, the photoelectric effect is challenging to achieve with infrared radiation. This is because the vibration frequency of infrared radiation is lower than that of visible light. As mentioned earlier, for the photoelectric effect to occur, the frequency of light vibrations must exceed the work function of the material. Therefore, as the frequency of light vibrations decreases, the likelihood of the photoelectric effect occurring diminishes. The vibration frequency of infrared radiation is approximately 1/10 that of visible light. Consequently, the vibration frequency of infrared radiation is much lower than the work function of metals. Therefore, it is difficult to induce electron emission from metals using infrared radiation. Of course, the photoelectric effect can still occur with infrared radiation. However, unless the vibration frequency of infrared radiation is sufficiently higher than the material's work function, the photoelectric effect may not occur or may happen very weakly. For instance, if the work function of a metal is 1 electron volt, then the vibration frequency of infrared radiation would need to be 10 electron volts or higher for the photoelectric effect to take place. However, the typical vibration frequency of infrared radiation is generally below 1 electron volt. Therefore, inducing electron emission from metals with infrared radiation is challenging. On the other hand, in materials with low work functions, such as semiconductors with work functions typically below 0.1 electron volts, the photoelectric effect can occur with infrared radiation if the vibration frequency is above 0.1 electron volts. Therefore, for the photoelectric effect to occur with infrared radiation, 2 conditions must be met. The frequency of light vibrations must exceed the material's work function. The intensity of the light must be sufficiently high. If these conditions are met, the photoelectric effect can occur with infrared radiation,